Hello and welcome to Water Quality. In this video, I'm going to continue a ferric chloride example where ferric iron complexes with hydroxide, and we're describing this as both a complexation reaction and an acid reaction. So in the previous video, we solved for the Ka1 value, which is describes a reaction that's shown here. So I'm showing the acid reaction where ferric reacts with water and releases a hydrogen ion. And this is described using a Ka1 value of 10 to the minus 2.16. So in this video, we're going to get the Ka2. So first, we're going to start out with the complexation reactions, and I'm going to write those out. So the first one is where the ferric is reacting with a single hydroxide. So I have ferric iron ion reacting with a single hydroxide. It's a reversible reaction and forming an iron hydroxide complex, the 2+2 charge. And this is described by beta 1, which has a value of 10 to the 11.84. And I'm getting these values from the water chemistry book by Snoyank and Jenkins. And then the second complexation reaction shows ferric iron reacting with two hydroxides, again reversible, and having a plus +1 charge. And this is described by beta 2 having a value of 10 to the 21.26. Okay, so what I want to do is get the second acid reaction. So first, what I'm going to do is flip the first reaction. So I have FeOH 2 plus goes to Fe3 plus hydroxide. And when I flip this, then I get an equilibrium constant that's 1 over beta 1, or 10 to the negative 11.84. And then I'm going to add 2 to this flipped reaction. Okay, so when I add the second reaction, I can see that one of the hydroxides cancels out. The iron complex cancels out, and I'm left with, let's see, I'm left with, actually, yeah, let's see, okay, FeOH 2 plus hydroxide, and then it goes to the other complex, so FeOH 2 plus. And then when I do that, I'm going to have beta 2 over beta 1, because when we add two reactions together, we multiply their equilibrium constants. And so now I have a reaction that describes kind of the partitioning between these two complexes. And next, I'm going to add the water equation to this. So I have Kw, and I have water going to hydrogen ion and hydroxide. And so when I do that, I get the FeOH 2 plus water. The hydroxides are going to cancel out. And then FeOH 2 on the bottom, plus on top. And I have the hydroxide, or sorry, the hydrogen being released. And this, as you can see, is an acid reaction because of the release of the hydrogen ion. So that's the whole point of an acid reaction. And so we're going to call this Ka2 because it's the second acid reaction. It's where It's basically where ferric iron acquires a second hydroxide, and the again, we're going to multiply the equilibrium constants when we add two reactions together. So I get beta 2 times Kw over beta 1. And my beta 2 is 10 to the 21.26. And then Kw is 10 to the minus 14 over beta, which is 10 to the 11.84. And this gives me an answer of 10 to the minus 4.58, or a pKa2 value of 4.58. And what this means is that for pH that are less than this value, 4.58, our acid form will be dominant, and the acid form is the FeOH2 plus is dominant. And where the pH is greater than 4.58, the base form, or FeOH2 plus, is dominant. So we're only considering these two species here. If we slide up or down the pH scale, we'll have to include other species, but only in considering these two species here. So for further analysis of this complexation system, we're going to go to another video and look at that.